All right, thank you very much, Brett. So this is a presentation of work that I've been doing for the last about 6-7 months now. I was supposed to present this at the Central Iowa Severe Storms and Doppler Radar Conference, and unfortunately we had to postpone it this year due to the COVID-19 outbreak. So one thing that I do want to note here is that because I was on the planning committee for that conference, as it's our local chapter here, a lot of the work that I was hoping to have done wound up not getting done. And the other thing too, with having to telework over the last 4.5 weeks now, I haven't had access to my AWIPS workstation at the offices frequently, especially with the amount of telework that I've had to do. So, but nonetheless, I'm hoping to have the opportunity to gather some feedback about the potential ideas that we have for the research project that we're hoping to forge ahead with in the coming months, and probably looking now into next academic school year. So as the title would suggest, there are going to be two components to this presentation. And so the first component was more meant to be for the students that were going to be at the Severe Storms and Doppler Radar Conference. But I'm going to go ahead and present the points here because it was still interesting to look at it. But essentially what we were asking ourselves in the discussion that we were going to have would be the benefits of moving to a 3 to 4 kilometer convective allowing model solution for our mesoanalysis page versus using a coarser resolution model. And so a lot of this discussion stems from the current use of the 40-kilometer wrap field that we use with the Storm Prediction Center's mesoanalysis page in most of our events. So the second half will be more of the research project that we'll actually be moving forward with, essentially looking at our ability for operational models to determine what is that near surface source of vorticity, and are we able to capture that well, specifically looking at the 0 to 500 meter storm relative helicity output that we have from both the HRRR and the WRAP. So we'll start off with part one, and we're going to look at a somewhat difficult low-top supercell environment, at least from Des Moines' perspective. This was a little bit more clearer for Northeast Kansas, but on May 21st and 22nd of 2019 last year, we had low-top supercells that moved from Northeast Kansas into portions of Northwest Missouri and then eventually into Southwest Iowa, where we had a brief spin up, but it wound up producing an EF2 tornado in Adair, Iowa, that unfortunately resulted in 2 fatalities. So while we look at this event, when we're trying to compare our CAM output of around 3 to 4 kilometers in our grid spacing versus 13 kilometers, we're going to be looking at the 0 to 500 meter storm relative helicity, since we have other work that is looking to focus on this. And so we'll go ahead and just put the key points up front here. Is that what we'll notice in this analysis here is that the amount of detail that is available between the 2 different models. And then the other thing is that if you're a dedicated mesoanalyst in a severe weather environment, that you really don't want to be relying just on one source of some kind of model output or model analysis. So these are the plots that I have created. On the left-hand side will be the 0 to 500 meter storm relative helicity from the HRRR. I took this from the HRRR archive available from the University of Utah. And then on the right-hand side will be the 13-kilometer WRAP analysis. And so this is well before we had initiation for the event. But the one thing that you can tell first off, right off the bat on the right-hand side, is that the WRAP is definitely a little bit coarser. It's a little bit smoother, and you don't have as many fine of the details as you do as with the HRRR. So the one thing to keep in mind with this particular event, we're actually going to be focusing on Northeast Kansas and into Southwest Iowa here. We did have a low-level jet that was going through the warm sector at this time here in Missouri, but we actually didn't have we had mostly stratiform precipitation along the isentropic ascent that was here. So eventually we're going to be focusing on Northeast Kansas up into Southwest Iowa here as this event unfolds. So one thing that we notice is that as we step through the next couple of hours here is that we are starting to see our storm relative helicity in the near surface layer increase right along an occluded boundary that we have at this time, probably close to the Kansas-Nebraska state line here. And so at this time, we can see both the models are starting to depict an increase into Northeast Kansas and Northwest Missouri here with our storm relative helicity. Typically for tornadoes at this particular layer, the 0 to 500 meter layer, we're going to be looking for values anywhere between 90 and 150 meters squared per second squared to have the chance for tornado genesis. And as we go further into the afternoon, we continue to see those amounts increase here. The one thing that I want to point out with what the HRRR is doing, though, is that we're starting to see convection initiation occur. And we're getting more robust, we're getting higher values with our HRRR output than we are with our WRAP output. And this is likely due to the fact that the HRRR has the ability to nearly resolve our individual updraft. So the one thing to keep in mind is that even at 3 to 4 kilometers, we're not necessarily resolving every single updraft that is occurring. But as a result of that, we actually are getting more robust values here in our HER output than we are in the RAP output. And so now as we go into 22 and 23Z here in the afternoon on May 21st, getting ready to go into May 22nd here, we can see again that the values really are starting to ramp up here in portions of Northeast Kansas based on the HER. But if we look at the RAP, the values are a little bit lower. But the one good thing is that if you're using the RAP as a mesoanalyst in this situation here, you're still looking at values that are over 120 meters squared per second squared, which would certainly have you concerned about any kind of surface-based convection being able to produce a tornado here. But again, the HER is doing very well with picking up on these individual updrafts here and actually indicating here that, hey, the storm is probably modifying your environment and giving you more storm relative helicity. So then as we get into 0Z, at this time, we actually have tornadoes here that are on the ground, and we had a few confirmed tornadoes that were occurring in portions of Northeast Kansas. So once again, this was in the Topeka CWA. And the HER now at this point is indicating that we have storm relative helicity values over 230 meters squared per second squared, where the RAP is still indicating that we have values that are favorable for tornado genesis, but at this time, it's not necessarily giving us the same exact detail as the HER is able to give us. And one other thing that I want to point out is that I'm just using bunker storm motion. So this is essentially the storm relative helicity output directly from the HER here. I haven't made any adjustments to the surface wind field or to the storm motion. Had I done that, we would actually probably be getting some higher storm relative helicity values, at least from the HER output. And if we incorporated that into the RAP, we probably also would see a modest increase in the RAP output. So as this convection is ongoing, we did have a little bit of a lull between 1 and 2Z at this time as the storms are moving in portions of southeast Nebraska and northwest Missouri here. But we can still see that the HER, even in the storm relative helicity plots, appears to be resolving these storms and shows us these areas of enhanced storm relative helicity. Meanwhile, where the RAP still is giving us high values, but isn't necessarily showing us that enhancement. Then finally, as we go closer to 6Z, this is right around the time when we had the EF2 tornado occur in Adair. Adair is going to be right in here. This is where we had storm relative helicity values that once again quickly increased to over 230 meters squared per second squared, with the RAP indicating values around 150. So again, the RAP is indicating to us that, okay, yeah, there's probably good potential for tornado genesis to occur if we have surface-based convection, but it's not necessarily resolving those fine details that we are getting in the HER. So the next set of plots that I have, we'll take a look at the RAP. So the left-hand side will be the output reflectivity, or simulated reflectivity, and the right-hand side will once again be the storm relative helicity plots. And so the one thing that I'm making a point with showing these plots here is that the RAP at 13 kilometers here, it takes pretty intense convection or rain showers to really start having an impact on what is happening in the storm relative helicity field. And so as this is ongoing, we can see that the values, especially here in Southwest Iowa, remain relatively unchanged as some of this weaker convection is ongoing. And it's not until the stronger stuff moves through when we actually start to see a drastic change here. So that's one thing where something like a coarser resolution model, such as the RAP, may be able to help, is that if you have spurious convection going on, it still actually may be able to maintain some of the better attributes of the environment, especially if that convection never occurs. Now, if we take a look at the HER, which is going to have a better ability to resolve a lot of our storm-like features here as we go on in time, as these storms initiate here right along the Kansas-Nebraska border, we're also getting our increases in our storm relative helicity. But we can also see how the storms are changing the environment and thus giving us the better detail for the potential for tornado genesis here. And then as we go in, so this was eventually the storm that would go on to produce the Adair tornado here. And again, these were associated with the values that were well over 230 meters squared per second squared, and honestly, probably higher if we actually go in and change our surface wind vector and account for any storm motion that may have been slightly different than the bunker's storm motion. So the part one summary that we have is that the 3 kilometer HER analysis really helped to narrow the areal extent for favorable for tornado genesis based solely on the 0 to 500 meter storm relative helicity field. In this particular case, though, the RAP 13 kilometer analysis did still provide a useful picture of our low level shear environment. But the one thing to note was that the occurrence of convection in the HER greatly influenced the environment. And so this is one note to the dedicated mesoanalyst in any severe weather environment, is to be aware of spurious convection that may be occurring in the model. If you have convection that is in the model but is not currently ongoing, and there's no sign that that convection is going to happen, you may need to consider just completely dismissing that solution here. So the point for the dedicated mesoanalysis here is that you will probably need to be using a combination in the future of finer resolution analysis with coarser resolution analysis. But again, we don't want to be focusing just on one particular model analysis when we are dealing with these kind of trickier convective environments. So for the second part of my talk, this will be the research project that we're going to be pursuing further here. And so the motivation from this comes from a lot of the high resolution simulations we've had over the last decade that are pointing towards the near surface layers being a key source of vorticity for tornadogenesis. And we've had the whole argument of, is it forming from the top down? Is it forming from the bottom up? Maybe we have a combination of both here. But either way, these high resolution simulations are showing us that we really need to be focusing on some of these lower levels. And so Bryce Kofer and Matt Parker at North Carolina State had a really good paper that came out last fall that found improvements to the significant tornado parameter when they incorporated the 0 to 500 meter layer storm relative helicity over using either the 0 to 1 kilometer or using an effective layer. And it was also recently announced that the 0 to 500 meter storm relative helicity will soon be available on the SBC mesoanalysis page. So the one thing to keep in mind is that these idealized simulations are, have a lot of grid points within the 0 to 500 meter, within that 0 to 500 meter layer. And so the HER and the RAP do have the ability to put out a 0 to 500 meter storm relative helicity value, but there are a few concerns that we will address. And that's essentially why we're looking to take this opportunity to develop an R2O initiative. So the problem that we've identified here mainly lies in the fact of the grid spacing that is available in an idealized model domain, such as Cloud Model 1, versus what we would use in the HER or the RAP. And so for our convective allowing models that we're using operationally here in the Weather Service, is we're only typically on a good day are going to get 3 to 4 grid points in that 0 to 500 meter layer. And so the question that we're asking here is that, is 3 to 4 points really enough grid points to resolve features that are within the turbulent boundary layer? Typically for a lot of features, we're looking to have 9 to 10 grid points to be able to adequately resolve it. And so if we look at the work based on the idealized simulations that have been conducted in this decade, the answer to that would likely be no, as important changes are happening over very small increments within that 0 to 500 meter above ground layer. And so the other thing to keep in mind is that if there are these small processes that are ongoing that we're not necessarily capturing, that could have pretty critical implications for both our photographs and our storm relative helicity computations. It would also include impacting the calculations for a critical angle. So here is what it would look like for our photographs here. And this is just one that I drew up, but made it idealized. So the red lines here represent our 0 to 500 meter layer. And so we draw in a right moving storm motion, our storm motion vectors. We can also see where we have our horizontal vorticity, where we're going to be looking for our storm relative helicity to be parallel to that. And then so we draw the rest of our storm motion vectors, and that area highlighted in there is what eventually gives us our storm relative helicity. But again, if we're not having enough grid points to adequately resolve this, we may be having some issues here. And so the black points that I have on this particular photograph are points that are supposed to represent grid points in our current CAM model, such as the HER. But the idealized simulations that have been ongoing have indicated that these points that I have here in the orange would also be important points to have in the photograph to actually adequately capture a lot of these boundary layer processes. So this here again is the figure that I showed just a few slides back about what the grid points look like. And there's a few things that we could try to do with our current operational CAMs to try to essentially put more points in there. And a lot of those usually involve some kind of statistical method or interpolation method to improve the storm relative helicity calculation. And one of the most common things to do within the convective boundary layer is to assume a log wind profile. And so that can be good in some cases, but the problem is that it's not necessarily based in physics here. And so if we take that previous example here and we add more of our grid points by some statistical interpolation method here, this is what the photograph can do. And so overall, this does okay with giving us essentially providing more definition to the photograph here, and maybe provide some kind of enhancement to our storm relative helicity. But the one thing to keep in mind is that if we're assuming like a log wind profile in the boundary layer, we're not necessarily explicitly calculating the wind at each grid point. So we're ignoring our Navier-Stokes equations and everything else to actually physically calculate the wind. We're simply just using a statistical method and saying this is likely what the wind is between the current grid points that we have. So the work that we are hoping to be able to accomplish here is to conduct a WRF simulation with the University of North Dakota. And our goal is to utilize a nested vertical domain within the WRF that should hopefully be able to place 7 to 8 grid points in that 0 to 500 meter layer and allow us to actually explicitly calculate the wind at each one of those levels and give us a good idea of what our 0 to 500 meter storm relative helicity would be, and essentially be able to determine if we're able to actually capture the important near surface source of vorticity that we may need for tornado genesis. So the main research question from the Weather Service perspective that this will eventually answer is, will a WRF parameterized with an operational framework be robust enough to adequately depict that near surface layer and thus capture that near surface vorticity source? Again, it's a lot of our operational models are different than these idealized models in terms of the microphysics that they use. And so we want to know is, does an operational framework model have the ability to actually resolve this if we throw more grid points and a little more computational power at it here? And so ultimately, we want to compare this operationally configured model with increased grid points to those from the idealized simulations. And then ultimately also determine the current reliability we have from our cams, such as the HRR with the 0 to 500 meter storm relative helicity output. Is having 3 to 4 grid points good enough where we can trust that, or do we need to be doing a little bit more if we're actually going to try to adequately resolve our near surface sources of vorticity? So these here are my acknowledgements. The MetPy is where I create a lot of the plots. I got the HRR data from the Meso West archive from the University of Utah. Dr. Kathy Finley will be the one that we will be working with at the University of North Dakota once we're eventually able to start running these simulations. And that is all I have. Thank you very much.